Welcome back to Daily Dose of Space. Most planets live quiet, predictable lives. They form from disks of gas and dust, orbit their stars for billions of years, and if they're lucky, they remain largely unchanged until the star itself runs out of time. But some planets don't follow that story. Some planets exist in places where, according to everything we know, they should not exist at all. They orbit stars that are already dead. Stars that have expanded, collapsed, and violently transformed. Stars that should have erased everything around them. And yet, somehow, these planets are still there. Today, we're exploring one of the strangest discoveries in modern astronomy, a planet that appears to have survived the death of its own star. Not as science fiction, not as speculation, but as a real object observed by real telescopes, forcing astronomers to rethink what planetary survival actually means. Because if a planet can survive the end of a star, then the story of planetary systems may be far more violent and far more resilient than we ever imagined. What it means for a star to die. To understand how strange this discovery is, we need to understand what normally happens when a star reaches the end of its life. Stars like our Sun spend most of their existence quietly burning hydrogen into helium. This phase lasts billions of years and is relatively stable. Planets form, climates settle, orbits remain predictable. But that stability does not last forever. When a star like the Sun runs out of hydrogen fuel in its core, gravity begins to win. The core contracts, temperatures rise, and the star starts burning new elements. As this happens, the outer layers of the star expand dramatically. The star becomes a red giant. In this phase, the star can grow hundreds of times larger than its original size. Inner planets are often swallowed entirely. Others are scorched, stripped of their atmospheres, and violently reshaped by intense radiation and stellar winds. Eventually, the outer layers of the star are blown away into space, forming a glowing planetary nebula. What remains at the center is a white dwarf, a dense, Earth-sized remnant containing roughly the mass of the original star. From a planetary perspective, this process is catastrophic. Orbits shift, gravity weakens, radiation spikes, shock waves propagate through the system. According to classical models, the inner architecture of a planetary system should be completely erased, which makes the next part deeply uncomfortable, because astronomers have found planets where this didn't happen. The discovery that shouldn't have been possible. In the early 2000s, astronomers began noticing something strange around certain white dwarf stars. White dwarfs are supposed to be clean. Their gravity is so strong that heavy elements quickly sink beneath the surface, leaving behind atmospheres dominated by hydrogen or helium. But many white dwarfs weren't clean at all. Their spectra showed clear signs of metals, calcium, magnesium, iron, elements that should not be there unless something was actively delivering material onto the star. The implication was disturbing. These stars were accreting debris, not from interstellar space, but from their own planetary systems. Further observations revealed disks of dust and gas orbiting white dwarfs, remarkably similar to the disks seen around young stars. Except these disks were made of shattered planetary material. And then came something even stranger. In a handful of systems, astronomers detected evidence of intact planetary bodies orbiting white dwarfs, not distant survivors far from the system's edge, but objects in relatively close orbits. One of the most striking examples is a planet-sized object orbiting the white dwarf WD 1856 plus 534. This object completes an orbit in just over a day, placing it extremely close to a star that should have destroyed it long ago. According to standard models, This planet either should not exist or it should not be there. And yet, it is. How could a planet possibly survive this? At first glance, survival seems impossible. During the red giant phase, the star would have expanded far beyond the planet's current orbit. Any planet in that region should have been engulfed, vaporized, or torn apart by tidal forces. So, astronomers proposed an alternative explanation. The planet didn't survive in place. It moved. The idea is that the planet originally orbited much farther away. During the chaotic death of the star, gravitational interactions between remaining planets, or stellar remnants, could have scattered the planet inward, placing it into its current tight orbit long after the red giant phase ended. This explanation works on paper, but it creates new problems. For one, the inward migration would have been extremely violent. The planet would have experienced intense tidal heating, potentially enough to melt or completely restructure it. For another, the timing has to be precise. Too early, and the planet is destroyed. Too late, and the system lacks the gravitational energy to move it inward. There's also a more unsettling possibility. Some astronomers suggest that what we're seeing may not be a planet that survived, but a planet that formed again. A second-generation planet assembled from the debris of the original planetary system after the star's death. If true, this would mean planetary formation is not limited to young stars. It could happen again under radically different conditions long after a star has already lived and died. And that idea quietly changes everything. What this means for planets and for us. If planets can survive stellar death or reform afterward, then planetary systems are far more durable than we thought. It means that the end of a star is not necessarily the end of its system. It also raises uncomfortable questions about habitability. White dwarfs are faint, stable, and long-lived. In theory, a planet in the right orbit around a white dwarf could maintain stable temperatures for billions of years. But such a world would carry scars of unimaginable violence. Its history would include stellar engulfment, tidal distortion, radiation storms, and orbital chaos. This is not a gentle environment for life as we know it. And yet, the universe has a habit of surprising us. What we are really learning from these systems is humility. Our models work until they don't. Our expectations hold until a single object appears where it shouldn't be, orbiting a star that should have erased it. The planet around W, D1856 plus 534, is not just an oddity. It is a reminder that survival in the universe does not always mean avoiding catastrophe. Sometimes survival means passing through it. A dying star should erase everything around it, but at least one planet didn't get that message. And the most unsettling possibility is not that this planet survived against all odds, but that it may be telling us something much deeper about how planetary systems end, or perhaps how they begin again.